In this section, we shall be solving Euler homogeneous equations. Now, the first thing is to identify the type of equation. Whenever a differential equation can be written in the form f of t of y equal to f of y on t. If we are able to write a differential equation in this form, then we see that this differential equation is an Euler homogeneous equation. Now, one property of Euler homogeneous equation is that the equation is invariant. Whenever y is transformed by some constant c and t is also transformed by another constant c. So for example, if I should transform t and y in the form tc yc, then the derived function f is going to be, it means that wherever you see y, you multiply by cy, then the t will also be ct. Then finally, we will get back f of, remember that this function, the c can come out. When c comes out, we will get y, or cy ct. You can see that the c and the is division, so c and y, c and c will cancel out. Then we have y on t. So you could see that c and c will cancel out, and we are getting back the original expression. So that is what we call invariant. Invariant means the function will not change, the original function will not change if t and y is being transformed by a constant. That is the meaning. So whenever you have a differential equation such that when you transform the dependent variable and the independent variable by some constant and the differential equation remains the same, then it means that that differential equation is a homogeneous, that is, it is Euler homogeneous equation. So let's come back to our question. Now, in this question, looking at the question closely, you can see y plus 1 here. We can also see y plus 1 here. So the first thing is, I can let u be equal to y plus 1. Then it means that if I differentiate u and y plus 1 with respect to t, I will get u prime here. Then if I differentiate y with respect to t, I'll get y prime. If I differentiate a constant, I'll get 0. So you could see that u prime is equal to y prime and u is equal to y plus 1. So we substitute these two into this equation. So wherever I see y prime, I'll write u prime. So I have u prime is equal to t times y plus 1, which is tu, then plus u squared. Y plus 1 is u squared, all divided by t squared. Now, this differential equation is homogeneous of degree 2. Now, you can check it using this approach. You could see that the t is raised to the power 1. The u is also raised to the power 1. 1 plus 1 is 2. Here, the exponent, the degree is 2. Here, the degree is 2. So, it means that in every term, the degree is 2. So we can just go ahead and say that this is homogeneous of degree 2. But we can also use the normal approach. Using the normal approach, we can say that u prime is of the function t and y, which is given as tu plus u squared, all divided by t squared. Now I want to transform t to tc and y to yc. So it means that u prime will be tc yc. And if I do that, it means that here becomes ct cu plus cu, or because here is squared, here becomes c squared u squared, all divided by, then the t squared will also be c squared t squared. So we still have u prime into bracket tc yc should be equal to, what we need to do is to factorize. We can see that here there is c here, there is c here, there is u here, and there is u here. So we can multiply c times c becomes c squared. So let me write it. C times c is c squared, then tu plus, we have c squared and u squared, all divided by c squared and tu. So from here I can factorize c squared out, and I'll get tu plus u squared, all divided by c squared tu. And you can see that both the denominator and the numerator has the constant c squared. What it means is that the differential equation is homogeneous, and it is homogeneous of degree 2. The degree is 2, because you could see that the constant is raised to the power 2. So it is a Euler homogeneous equation with degree 2. So now that you have been able to ascertain that this is a Euler homogeneous equation with degree 2 because of the exponent here. The exponent of the constant is 2. Now the next thing is that we now take this, which is u prime should be equal to tu plus u squared, all divided by t squared. It means that we know that this differential equation is homogeneous. Therefore, if I should multiply this by 1, it will be the same thing. I will get the same value. But I can write 1 in different ways. If I write 1 as t over t, t over t is the same as 1. T squared over t squared is the same as 1. Any number divided by itself is the same as 1. So how can I write 1? Now let's take note. 1 is always written in the form 1 over t exponent the degree. You see that it is homogeneous of degree 2. So always t should be raised to the power 2. So t squared. So what it means is that instead of multiplying it by 1, I can multiply it by 1 over t squared on top. then over 1 over t squared down. All this is the same as 1. Now let us simplify it. U prime is equal to, if I multiply 1 over t squared through, I will get u over t for this part. Then I will get u squared over t squared, which is the same as u over t all squared for this part. Then all divided by t squared times 1 over t squared will be 1. So finally I will get u prime is equal to u over t plus u over t all squared. Now where we have gotten to, we can still make another substitution. So I can say that let v be equal to ut. Let v be equal to ut. If v is equal to ut, I can make u the subject. Then it means that u is equal to vt. Then I can differentiate u with respect to t. If I differentiate u with respect to t, I'll get u prime should be equal to, now remember these are two variables, so I'm going to apply the product rule. I will hold v and differentiate t. If I differentiate t with respect to t, I'll get 1. So I'll get v multiplied by 1, which is v, plus I'll also hold t and differentiate v. If I differentiate v with respect to t, I'll get v prime t. This is v prime t. So this is what I have. So you can see that I now have an expression for u prime. So coming back to this, wherever I see u prime, I'll write v plus v prime t. Then should be equal to u over t. We know that u over t is v, so v plus u over t again, so v squared. Then from here we can try and separate the variables. So let's try and separate the variables, because this differential equation is now in a separable form. So in doing so, I can, you know that there is v here, there is v here, so it will cancel out. Then you'll be left with v prime t should be equal to v squared. I can divide through by v squared. I'll get v prime t over v squared should be equal to 1. Then I can divide through by t. If I divide through by t, or let me go back and show you another method. For it to be simple, change this v prime to the Leibniz version. So v prime can be written as dv dt. That's the meaning of v prime. Then it is multiplying t here should be equal to v squared. So the first thing is multiply through by dt. If I multiply through by dt, I'll get dv t should be equal to v squared dt. So that's I'm multiplying through by the t. Then the next thing is divide through by v square. If I divide through by v square, I'll get 1 over v squared dv. Then I'll divide through by t2. So I'll get 1 over t dt. So you can see that now all the v's are on the left hand side and all the t's are on the right hand side. So we can simplify this one. We can now simplify or integrate this one. So let's move on. We have 1 over v squared dv should be equal to 1 over t dt. What we have to do is to integrate both sides. Now we can do the integration easily. We know that 1 over v squared can be written as v exponent negative 2. And if I integrate this, I'll get add 1 to it and divide by negative 1. So I'll get v exponent negative 1 over negative 1, which is the same as negative 1 over v. So that is for the first part. I'll get negative 1 over v should be equal to, but if I integrate 1 over t, I'll get the natural logarithm of t plus your arbitrary constant of integration. So the next thing, let's go back and see something. Remember that v is equal to u on t. V is equal to u on t. Let's write that one down. V is equal to u on t. Then also, let's take note that u is equal to y plus 1. U is equal to y plus 1. So we are going to do the substitutions here. So it means that wherever I see v, I'll put u over t. So I have negative 1 over u over t should be equal to ln t plus c. And this whole thing can be written as negative t over u should be equal to ln t plus c. But we still have u to be y plus 1. So we have negative t over y plus 1 should be equal to ln t plus c. Then from here we can reciprocate. When I reciprocate, I'll get y on top, y plus 1 on top over negative t down. Then I'll also reciprocate here, which will give me 1 over ln t plus c. The next thing is to multiply here by negative t and here by negative t. So I'm going to get y plus 1. Y plus 1 should be equal to negative t all over ln t plus c. Then I can make y the subject. Y is a function of t. So yt should be equal to negative t, or let me put it this way, negative t over ln t plus c. Then this one goes there to be minus 1. And that is the solution to the Euler homogeneous equation. Goodbye.